Professor Haigh is an atmospheric physicist and for 5 years a co-director of the Grantham Institute on Climate Change and the Environment at Imperial College London. Previous to that, she was the head of Imperial's physics department. She has been a lead author for the UN Intergovernmental Panel on Climate Change and shares a Nobel Peace Prize with several hundreds others for that work. With that, I ask you to give your full attention to Professor Joanna and help me welcome her. Professor Joanna.
Thank you, Sarah, and thank you, Dawson, for the invitation. So I'm going to talk about climate change. So this definitely, you studying climate definitely involves physics.
Sorry, Professor Haigh, I think you're on mute.
I am, thank you very much. Start again. I'm going to talk about climate change, which involves a lot of physics. It may be not the sort of physics that many of you are familiar with. It may not be what you might call theoretical physics, but there's a lot of theory in there. And it's certainly something where you can apply your physics knowledge to something that's of real global importance. So if I can get going here. So this is the background of what you might call climate change. And this is the global average surface temperature over the last 170 odd years. And you can see it's wiggling around. Each of the red spots is the average temperature, and the vertical line through it is the 95% confidence intervals on those values.
Sorry for interruption, but we can't see the screen.
Oh. So we tried it before and it worked.
Yep, so if you just click the share screen and then you should be able to select.
I did.
Oh, and it's not working?
No.
Okay, that's really odd.
I'm sharing screen 2 and that's screen 2. I've got my thing on.
Have a look. If you can just end the share screen, please.
I can't see the thing that says end share screen now. Perhaps I'll end the talk.
Okay, yeah, and then if you rejoin, we can just let you back in, if that's easier. Thank you, sorry about this.
I don't know what's happened, because it was funny, wasn't it? It was working before.
It was working.
Right. Escape. I can't get it off now. Oh
What's
dear.
on the screen right now? Is it just the slide that you're sharing?
So now wait a minute, I'm turning everything off. I've got all my PowerPoints off. So I'll start the PowerPoint again.
Mm-hmm. And then if you just go onto the Zoom call.
Yeah.
And down below, there should be a green share screen if you click that.
Hang on. Yeah, this is what we did before. Then I click on the correct one. Yeah, share.
Yep. There we go. That's
okay.
Perfect.
So now I've got to get the thing going.
Yeah, thank you.
Right. Can you see it now?
Yeah, good.
Hooray. Sorry, everybody. Right, I won't do the intro again because I've already said all this. So this is the global average temperature graph. It's showing the global surface temperature over the last 100, and it's overall increased by more than a degree since over that period. You can also see from here that the uncertainty bars are getting smaller, so they're quite large up here, but they're quite small up here. But the overall picture, which is of course what's become known as global warming, is this upward trend in temperature over that period. So we want to understand why that's happening and how that is reflected in changes over the globe. So here's some very basic physics. All the energy driving the climate system comes from the sun. There's a tiny little bit that comes out of the center of the Earth, but most of it's coming from the sun. So that's solar energy. I'm sorry about my graphics, it's not one of my skills. Comes to the Earth intercepts the radiation from the sun and warms up, gets hot, and emits radiation. heat radiation. And if you work out the balance between the solar energy absorbed and the what the temperature of the Earth must be as a black body to emit the same amount of energy to space, you get the answer as -18 degrees Celsius. So you might think, hang on a minute, she said it was easy physics, but now look, she's got the wrong answer. Certainly the temperature of the Earth's surface temperature is not -18 degrees Celsius. But of course, what I haven't considered in this simple calculation is the fact that the surface temperature is affected by the atmosphere. So this picture here is showing what happens to that radiation coming in and out of the atmosphere. So we've got the solar radiation in yellow, as it was in the previous picture, coming in at the top of the atmosphere. Some of that's reflected back to space, some of that's absorbed within the atmosphere, and about half of it gets to the Earth's surface and gets absorbed. And then the Earth's surface gets warm, and then you get this red bar, which is the heat radiation coming out. But while the atmosphere is semi-transparent to solar radiation, it's very absorbing of heat, infrared radiation. And so it's pretty much all absorbed. Then the atmosphere gets warm, and that emits heat upwards and downwards. And so what you've got coming in now is this extra energy source coming into the surface, and that's what's called greenhouse effect. It's a bit of a bad name, unfortunately, because greenhouses don't really work like this, but never mind. So what we've got is the greenhouse effect. It's perfectly natural. It's been happening in the atmosphere forever, and it makes the surface about 30 degrees warmer than if there were no atmosphere there. And so it's the greenhouse effect that's actually responsible for us living on a nice habitable planet. So why would climate change? And you can think of natural factors, and you can also think of factors due to humans. So natural factors would be if there were changes in that incoming solar radiation. If the sun suddenly started putting out more radiation, that would warm the planet. Volcanic eruptions. So if you get a big volcanic eruption, it chucks a whole load of stuff up into the atmosphere that can, if it gets high enough, it can stay there for a couple of years. And you can measure actually cooling after big volcanic eruptions. And then, of course, this is not climate change so much, but you have to understand that it's a complex system. And so you're bound to get internal variability, you're bound to get noise in the system. So the temperature will go up and down just because it's sort of sloshing around in a natural sort of a way. Then if we look at the human factors, as I've already alluded to, there's greenhouse gases in the atmosphere, and I'll go on to those in a minute. And if you increase greenhouse gases, you increase the greenhouse trapping of heat radiation, and that causes the surface to warm. If you put particulate pollution up into the atmosphere, so particularly if you put sulfates from power stations, for example, they can act a bit like those volcanic particles. They float around in the atmosphere, they reflect the sun's radiation back to space and have a cooling tendency. And then you can have other effects like changes in land use. So if you were to chop down a lot of trees and you get a more bright desertified surface, that's brighter, and then again that reflects sunshine to space, so that will tend to cool the planet. So you need to take all of these things and more into account when we think what's causing climate to change. So what are the gases in the atmosphere? As you will be well aware, it's pretty much 80% nitrogen and 20% oxygen, but a little bit of many other gases. But the ones that are of interest are the greenhouse gases. So nitrogen and oxygen have essentially no greenhouse effect. They don't absorb infrared radiation at all. So the ones that do are water vapor. That's the most important one, which of course is very variable depending on where you are over the globe and also where you are in the atmosphere. The next most important one is carbon dioxide, and its concentration is about 400 parts per million. That means 400 molecules in a million, or 4 in every 10,000. Then we have ozone, which again is very variable in concentration. And another greenhouse gas is methane. And there's others that I haven't listed here that are also important. So these are the ones that we're going to be interested in, what happens when they change. So if we look at the spectrum of heat radiation leaving the top of the atmosphere, so what I've got is, this is in equal energy area map. So it's in energy or frequency units across the bottom there. And at the top, we've got the wavelengths of the radiation. So you can see this is the infrared spectrum. There's 5 microns there on the right, going across to 100 microns on the left. And if you had a surface at 21 degrees Celsius, that's the Planck curve in red there that you can see peaking at around 14 or 15 microns and less either side. So that would be what's leaving the surface. Note, this is not a global average now. This is a particular example. And what we got in blue there with the black line is the measured flux at the top of the atmosphere over the tropics. And you can see it's not the same as the emissions from the surface. It's very wiggly, and also there's big bites out of it. And this is the effect of these greenhouse gases. So you can see them labeled water vapor over here on the right and the left, carbon dioxide over this big bite in the middle, and ozone and methane. And they're causing less radiation to escape from the top of the atmosphere than is being emitted into the atmosphere from the surface. So this is the greenhouse effect. And we can calculate what each of those gases is doing. So what we've got here is the difference or the effect of those gases on the radiation leaving. So all of these values are negative because they're stopping some of the radiation leaving the atmosphere. And in each color represents a different gas. So you see we have water vapor in red, and that's impacting the atmosphere or the climate by about 70 watts per square meter. And that's within a global budget of about 240. So that's a significant amount. And that's the largest greenhouse gas. The next most important one is carbon dioxide. Now it's I don't know, luck of the draw, or perhaps it's something to do with my molecular vibrations. Well, I'm sure it is. But the fact that water vapor just so happens to absorb in places where carbon dioxide doesn't, and the other way around. So we've got this big effect of carbon dioxide over a much narrower spectral region, but a big bite coming out here. And that's the carbon dioxide effect, and that's responsible for about 25 watts per square meter. And then you can see there's other gases having a smaller effect. So if we subtract off each of those from the, oh no, I haven't done that, never mind, go back again. So what we've got is each of these gases is responsible for different absorptions across the wavelength spectrum. And as we increase these gases in the atmosphere, they will absorb more. And we could talk about the physics of that in more detail, but I want to get onto more about the impacts. So what happens when these changes? Now, obviously, water vapor is very variable over the surface of the Earth, but its total content is limited by the fact that it condenses out. So if it gets too much, it just rains or snows and it precipitates out. So it's actually constrained by the temperature. Whereas other gases like carbon dioxide, if we put some into the atmosphere, it just stays there. And so we put more in and it stays there and it accumulates. We can't do that with water vapor. So with some of these others, human activity certainly can. And the one that's having the most effect is carbon dioxide. So what we've got here is I'm going to show you several graphs, each of which is showing atmospheric carbon dioxide concentration as a function of time. Now you see this axis here is hundreds of millions of years. That's a very, very long time. I've put here first primates evolved on Earth here. So that's just about 15 million years ago or something like that. And you can also see marked here 400 parts per million, which is the current concentration of carbon dioxide. This plot at the bottom here is hundreds of thousands of years going up to 400,000 years ago. And you can see the 400 parts per million is now well above the top of that graph. I've also identified when modern humans evolved, which is something like 200,000 years ago. So when carbon dioxide was well below what it is today. And then I can show you more plots. This one is over 10,000 years. And you see the CO2 is fairly flat, perhaps a small increase. And now we've got 1,000 years. It's fairly flat until we get near the end and suddenly it goes. And that little red graph there is from atmospheric measurements made in a clean air observatory at Hawaii. And you can see the unremitting upward trend. The wiggle's annual cycle, so it responds to the amount of vegetation on the globe, which of course has an annual cycle. But you can see that the 400 is up here and it's just been going up and up and up and it's continuing to go up and up. And we know that's due to human activity for several reasons. One is the isotopic content of the carbon is such that it's clearly coming from fossil fuels. Secondly, if you do very careful measurements of the oxygen content of the atmosphere, it's going down a very tiny bit. That's nothing to worry about in itself. It's going down a tiny bit because it's being taken up in making carbon dioxide. So we're quite sure that this is due to the burning of human activity and burning of fossil fuels. And you can see that the carbon dioxide now, at over 400 parts per million, is larger than it has been for perhaps 3 million years, and certainly well before humans developed or the life on Earth as we know it now developed. So it is very unusual. If I just look at that 100,000 years time scale again, that was the carbon dioxide plot I showed you just now in red. And you can also see a temperature plot here. And it's very clear that the temperature is going up and down just like the CO2. And sometimes you may hear people say about climate change, oh, CO2 and temperature have gone up and down before. It's perfectly natural. And so what are you old climate extremists going on about? It's perfectly natural. Well, for a start, we've already noticed that the today value up here is definitely unusual. But the other thing is, this is, you can explain this actually to do with changes in the Earth's orbit around the sun. So what happens is, if the Earth's orbit is elliptical around the sun, and the actual value of the ellipticity, so how oval the orbit is, varies very, very slightly on 100,000 year timescales. So if you get a situation where the temperature goes up a little bit, then you get release of carbon dioxide and other greenhouse gases, particularly methane, from stores in permafrost and oceans and other places. So you get a little bit of warming due to the sun, you get the release of the greenhouse gases, you get more warming, you get more release, and then you get this very, very sharp increase in temperature until the solar effect turns off, and then very slowly it'll go back to where it was before. And these are the ice ages and the interglacials, and so of course they are perfectly natural, but you'll notice that the temperature changes, which are something like 5 or more degrees, come about with due to the changes in the greenhouse gases. So it's not reassuring that it's all happened before. It's rather, oh dear, we can see what the greenhouse gases are going to do. So I've just said that. So if we look at that, if we look at the rate of warming, at how fast it's warming coming out of an ice age, it looks quite sharp on this graph. But if you actually look at the numbers, it rises about 5 degrees in 5,000 years. Now we look and see what we've been doing to the atmosphere. It's risen by 1 degree over the past 100 years. So that is 10 times as fast as any natural sharp changes in the past. So while we are going to have to, we and all the animals and plants on the Earth are going to have to adapt to climate change, and we will be adapting, it's much, much faster than anything has adapted before. So let's do some physics. Those of you that do a lot of geophysical fluid dynamics will find this fairly easy, but for those of you that are not familiar, then perhaps this is helpful. So laws of physics in the atmosphere, we've got Newton's second law. What are the forces that are acting on a mass of air? Well, we've got gravity, pressure gradient. So if you think of a surface pressure weather map, you've got high pressure and low pressure, and the air will try to go from the high pressure to the low pressure. But you've got the effects of the Earth's rotation, which are influencing where it can go in that rotating frame of reference. And then you've got frictional forces as well. And we can write that down in this term. So that's the acceleration, that's gravity, that's the pressure gradient, that's the Earth's rotation called the Coriolis acceleration, that's rotation, and frictional forces there. This is a vector equation, so U has 3 components. Next law, conservation of mass. So you can say if you've got a volume of air, what goes in must come out or get squashed. We write that down like this. So that's the divergence of the air coming in and out of the volume. And this is rho is the density, and that's it getting squashed. Then we have conservation of energy. So if heat is added, the air will get hot or it'll expand. We write that like this. So here's the heat getting added, here's it getting hot, and if P is pressure, here's it expanding. And finally, I've got an ideal gas law, so relation between the thermodynamic variables, which I've written in this form. So I've got the pressure, the density, and the temperature. So in that way, we have 6 equations for 6 unknowns, where there's 3 wind components, up, down, east, west, and north, south. And this is essentially lovely, simple, basic physics, and it's the fundamentals of computer modeling, which is used to do the forecast, weather forecasts, and also climate models. And so what we do is we solve these equations on a 3-dimensional grid, as you can see identified on the right here, and we can step forward in time and find out how the variables are changing. And of course, you've got to put in the things like the heat sources and the frictional forces and all these sorts of things. But you can see it's very easy to understand physics. It's just the representation of it on this grid that gets more complex. So, as I say, the physics seems okay. Why aren't weather forecasts perfect, given I've been going on about how simple it is? And of course, the climate system is not quite as simple as I've been suggesting. For a start, it's not a cubic grid. So you've got these beautiful, beautiful clouds and surfaces and everything that's very, very complex. So on the right here, you can see sort of an example of a grid over the UK. And as the computer power that's available becomes greater, then we can increase the grid size. And that's why the Met Office and the other forecasting agencies across the world just want bigger and bigger computers all the time, because they want to get their grid size smaller and smaller. But they're never ever going to be able to resolve. You see the fine detail of these clouds and surfaces in the picture at the top there. We've also got to resolve clouds processes, that's rain and all the rest of it, which is a whole additional complication. And then importantly, down here on the left, you can see it says initialization. Now, if you're going to do time stepping, you've got to start somewhere. Now, if you're doing a weather forecast, you can start from all the weather data that you've got over the globe today, and that's what happens. And the satellite data is coming, and other data sources is coming all the time into the Met agencies, and they're always updating their models so that it's up to date with what the best data is saying all the time. The initialization is very important for climate forecasts as well. Now, to see where initialization went wrong, this is in a weather forecast rather than a climate model. I guess most of you are too young to remember this, but in the UK, there was a huge thing that was referred to at the time as the Great Storm in 1987. And you can see some of the devastation that was wreaked in those photographs there. But it wasn't forecast by the UK Met Office because of missing data from the Atlantic. And the French Met Service did forecast it, and they had got the missing data from the Atlantic. So that's just an example of where the initialization of the model forecast was very important. I'll come back to initialization of climate projections in a minute. So you might ask, and people do, of course, how can computer models with limited skill in predicting the weather over more than about 10 days? So we wouldn't expect to do weather forecasts for more than a week or so. You may be familiar with the European Centre for Medium Range Forecasts, which is possibly, arguably, the best weather forecasting agency in the world. And they do 10 days. They also do seasonal forecasts, but this is the limit of their weather forecast, really. So if we have these models, how can we possibly think that we're going to forecast climate in 100 years when there's clearly limitations to the forecasts over more than about 10 days? And the answer to that is that we're not actually predicting the same thing. So with the weather, we're going to try and predict, what's the weather going to be in London next Tuesday, at, midday, for example. Now, with the climate forecast, we're not going to predict for London or for a particular date or a time of day. What we're going to say is, what is the typical climate going to be in the southeast of England in winter 2050 or something like that. So the climate models are predicting typical values over regions, so they're like a sort of what you might expect, whereas the weather is what actually happens. So back to this plot again, and of course the key question is, can we explain the shape of this graph going back this time, and also of course going back further? But this is the period over which we have as it were, scientific instrumented measurements. So we're back to this plot I showed up here with all the things that can influence the radiation budget, and the models include the effects of all the things that I mentioned before in what can influence the surface temperature. And so the climate models have to try and represent these processes. And here's an example of some model results compared with observations. Now, the observations on this plot is exactly the same as I showed you before, as a black line with a range of values over that period. And the model results are in colours. Now you see there's a great spaghetti of results over here. And each of those model runs was from a slightly different initialization. So this is where initializing the climate projections are important. So if you just change the sea surface temperatures in the tropics, for example, you'll find that at the initialization point, you'll find that the temperature evolution is in detail much different. But what you can also see is that spaghetti, the range of that spaghetti actually tracks the observations very well. So it's a big variation around the observed values, but actually overall it's doing a pretty good job at simulating what's happened over the past 100 odd years. And we can also do experiments with the model where we switch different forcings on and off. So the picture on the left is exactly the same as the one I just showed you. And the one on the right is the black curve is the same observational curve again, but the colours now, the models have been run, but with only the natural forcings and not the human factors. And you can see that while there's some agreement up to about perhaps 1960 or maybe 1930, but after that, the temperatures take off and the models just don't simulate it. These blips here, by the way, are big volcanic eruptions causing cooling periods, also seen in the data. So we can simulate the climate at least in terms of global temperature quite well, and we know that it's due to human activity. But what about regional variations? So I've been talking about global temperature, but of course, if you live somewhere in the world, you're not going to get the same thing as everybody else. It's going to be a very local effect. And this is observed changes in surface temperature over the 100-year period up to 2012. And you can see that while the global temperature has gone up by about 1 degree, which is here is a sort of middle red colour, over the globe, some parts, in particular land areas, large continents, the temperature's gone up by much more like 2 degrees. Some places it's gone up less. The white areas is where there's not enough data to say with any certainty. And in some places, it's actually decreased. So there's a very interesting area here over the North Atlantic where it looks like it's actually been cooling over that period. And the oceanographers are all very excited about trying to simulate that. And it seems to be something to do with the overturning circulation of the ocean and how it's responding to climate change. So if you live in South America here, you're having twice the whammy of the average warming. So I've talked about temperatures. What about other evidence? So here's another measure, the area of Arctic sea ice at summer minimum. So there's an annual cycle in sea ice, there's least in the summer, and there's a records of its area. And you can see 2 examples here in 1979 and 2011. You can clearly white is covering a much larger area there than it is in here, but you have to be careful of taking a sample of 2 to construct a trend. But here's the data at the top here. So at 1979 to 2011, that's that period over there. It's clearly declining. The other important thing about ice is that if you remove the ice, you get a darker surface. So there's a bright surface there, it's turned into a dark surface here, which means there's less reflection of solar energy, which enhances the original warming. So this is what we might call a positive feedback on the original warming effect. So that's sea ice. So that ice is floating on the surface. So if it melts, it doesn't contribute to sea level. But if you look at ice on land, so here we have continental ice shelves and glaciers. If those melt, the water goes into the sea, and that's what causes half of the sea level rise. these are just some pretty pictures of glaciers and Greenland ice loss. And here's a measure of sea level since 1880. And you can see there's an continuing upward trend here. And about half of that is due to the melting of ice on land. And about half of it is due to thermal expansion of the oceans. So you can imagine that as everything warms up, the water of the oceans warms up, it expands, it can't go sideways or downwards, so it goes upwards, and particularly up the coasts where it's going to be inundating and where a lot of people live. So this is sea level again. I talked to this, you've seen this plot already. So we got measures of CO2 and temperature. We also got measures of sea level shown in red here. And you can see that over that period, we had approximately 100 odd meters of sea level change in response to 7 degrees Celsius global temperature. So perhaps you can see now why we are very worried about more than a few degrees Celsius. You know, we're talking about 1 or 2 degrees warming. Even that is going to be a big impact. In equilibrium, it's not instantaneous. As the climate equilibrates to that warming. So something else that's talked about is extremes, weather extremes. So when we talk about, I've talked about averages here and there, but of course what actually impacts is extreme weather. So it might be very heavy rainfall, it might be particularly strong winds. In this case, we're looking at heat extremes. And in the plot down there is the observed summer temperature anomalies over the Northern Hemisphere. So obviously, if you look over a region like the Northern Hemisphere, and you look at the average is here in the middle, and then you've got some places are colder and some places are warmer. That's obviously what you would expect. These units are in terms of standard deviations. So how has that been changing? We've got a little movie here, I hope, with any luck. Yeah, it's going to do. And what we're going to see now is 10-year averages of the actual measured surface temperature distribution over the globe. You can see it's sort of wiggling around there. And now you can see by the 1980s, it's clearly shifting to the right. And what you get to, by the time you get to the early part of this century, you've got the global warming, which is the shift from where it was originally to the mean of where it is then. But you've also got a huge increase in extremes. So something that was 1 in 1,000 high temperature, so out here it's sort of 3 standard deviations, is now a 1 in 15 occurrence event. And if you remember summer 2018, which was very, very hot, that's going to be a normal summer by 2050. So it's the extremes that impact people and of course other living things as much as the averages. So if we think about what's going to happen in the future, the principal cause of global temperature rise, as I've discussed, is increasing concentration of greenhouse gases. So if we want to look to the future, we have to assume future greenhouse gases. And of course, that's far more difficult for me. I have to be economist and a social scientist and all sorts of things. So, but luckily, people do make estimates. But first of all, I need to talk about the different greenhouse gases. So if we look at the greenhouse gas emissions, that's over the past 100 odd years, just in fractions due to different gases. About 3/4 is carbon dioxide, 16% is methane, and then we've got a little bit of the other ones. And if we look where they come from in terms of economic sector, this is globally, 1/4 is from electricity and energy production, and about 1/4 from agriculture, and about 15% from transport. And industrial processes about 1/5, but that's across the globe, and it varies between different countries and regions. So if you're going, I'm not going to go through this graph, this slide, because it's far too complicated, but what we're looking at here is assumed changes in energy sources, seeing these different country colours here. This is what it was in 2000, the different components. So orange is oil and black is coal. And these are different, what are called representative concentration of pathways. Don't worry about it. It's just RCPs of different assumptions about different energy mixes by 2100. So that's what they are at 2100. And these are the different evolutions that are assumed to get you there. Now, one thing that's important to note is that emissions are not the same as concentrations. So what we got here is the range of these different emissions. The worst one that was in this study on the Intergovernmental Panel of Climate Change report is this blue one, which is called RCP 8.5, where the emissions are going up and up and up pretty much. And the best one they looked at was one where it peaked in 2020 and then went back to zero by about 2080. So those are the emissions, but you see that's not the same as concentration in the atmosphere. So here's CO2 concentration responding to those emissions, and it's whooping right the way up with the RCP 8.5. With the RCP 2.6, it's going up, but even when this is going down sharply and going to zero at the end of the century, it's still well above what it was at the beginning of the century. So that's because carbon dioxide is such a long-lived gas, you can't get rid of it very quickly. So looking at the temperature rise in response to those scenarios, this one here is the 2.6 scenario, and that's the 8.5 scenario, and the climate model's prediction of what the temperature is going to, global temperature is going to be by 2100. And you can see that this is from the Intergovernmental Panel on Climate Change called Fifth Assessment Report. It's very annoyingly not the same temperature reference as I was referring to pre-industrial temperatures before. So to get relative to pre-industrial temperatures, you have to add 0.6 of a degree. So this lower one here, it looks like it's gone up 1 degree, but it's actually gone up 1.6 degrees, even for that very careful scenario. And this one here is getting up more like 5 degrees at the end of the century, which is serious. And there's a range, of course, which depends on different models and natural variability and things. And these are the projections of temperature distribution and precipitation. On the left-hand side, we have the sort of best scenario, better scenario. On the right, this RCP 8.5 bad scenario. And as we mentioned already, it's not the same over the globe. In particular, there's a lot more warming in the polar regions than in other parts of the globe. And you can see temperatures changes here of 10 degrees, which are absolutely extraordinary. And over the continents, temperature changes of 5 or 7 degrees. So that is serious stuff. Precipitation, that means rain and snowfall, is much more difficult to forecast, but you see in this seriously bad case, there's some regions that get more rainfall, that's the blue here, tropical, and in particular the summer monsoon intensity in the Indian region is considered to be on the increase, and tropical storms over here. But if you look at the Mediterranean, in most of the models predict that it's drying out, and certainly the observations from this region suggest that that's already happening, where there's less rainfall in that region as the global temperatures rise. That's sea level. I'm just going to say it's bad, really not go into it, but there's a range here from sort of 0.3 to 2.5 with the different scenarios. This is meters sea level by 2100, and this is serious. A serious impact if you consider that millions of people over the globe live in cities that are very close to the coasts. Oh, this is what would happen in the UK, impact of 2-meter sea level rise, which is 2150 at the current rate. You can see that a lot of Europe here over the Netherlands and Germany and Denmark is underwater. That's the blue colours there, and around the east coast of the UK, of course. So I've talked about the physical aspects, but of course there's the sort of human aspects as well, and regional aspects, and these are very different over the globe. So this is looking at, this is a report of the European Environment Agency, and it's looking at different regions. So the regions here are identified by colours and what might be the particular impacts there. And again, I can't go into this in much detail, but you see, for example, if you look over most of Europe, which is in this green colour, you've got, this symbol means increased river flooding, increased temperatures, more forest fires, but actually less overall precipitation. If you look at the Atlantic region, which is this colour seen over here, you've got increase in severe storms, again, increase in river flooding, increase in sea level, and this means decrease in home heating requirements, which I suppose is a good thing. And you can see the other regions around here, the other symbols here. This is to do with biodiversity in the mountain regions. And this here, for the Mediterranean region, is insect-borne diseases. So there's different impacts depending on which region. So there's some good things. I'll talk about less home heating. There's one here that it may be that in this dark blue region of Scandinavia here, there's a greater agricultural productivity. So at least over the sort of next few decades. So the United Nations has been talking about climate change since, well, perhaps at least 1970 odd. And there's the Framework Convention on Climate Change, which meets every year. It has a big meeting every 5 or 6 years, but it has annual meetings to discuss what it should be doing, what the nations of the world should be doing about climate change. And there was one in Copenhagen in 2009, which we were all hoping would really do something, because it was becoming very clear then that climate change was happening, and it was maybe getting bad. The Copenhagen meeting was a terrible disappointment because absolutely nothing was agreed. And so when in Paris, there was a unanimous agreement of I forget how many countries, perhaps 195 odd countries, to do something. And the agreement was to keep global temperatures below 2 degrees by 2100, and actually to try and get it under 1.5 degrees. So that was a huge achievement, and it was we were all so pleased when that happened. But of course, that's now sort of 5 or 6 years ago, and we see what's happened since. Each country declared its nationally determined contribution, or NDC, of what it would do. And so the NDCs were added up together. And I'm going to go back to that in a minute. What this plot is showing is CO2 emission pathways, which you can do and keep warming limited to 1.5 degrees. So again, there's a spaghetti here because there's lots of different models, studies with slightly different scenarios and starting points, etc., etc. But you see that to get under 1.5 degrees by 2100, these have a peak in emissions of essentially by 2030, and declining to 0 emissions by 2050. And that's the basis of the climate talks that are going now. And if you delay the peaking, you have to do extraction of CO2. I might mention that if I have time in a minute later on. So you might hear about a carbon budget. And the idea of the carbon budget is that you've only got a certain amount of carbon you can burn before it gets bad. So if you consider that CO2 has a very long lifetime in the atmosphere, and also consider that global temperature rise is pretty much proportional to the total accumulated CO2. So you put the CO2 into the atmosphere, it just stays there, it accumulates, the concentration goes up, and then the temperature goes up too. And so to constrain global temperature rise below any value requires greenhouse gas emissions to stop. It's a very simple conclusion. There's a nice analogy here with a bath. You can think of the 1.5 degrees or 2 degrees or something, if you don't want the bath overflowing. So you carry on pouring it in and in, but eventually it'll overflow. You can have a deeper bath, but if you carry on pouring in, it'll eventually overflow. So you've got to stop putting the CO2 into the atmosphere to stop the global temperature rising. And the greater the current pouring into the atmosphere, the sooner you need to stop. There's a little drain pipe here showing net removals, a suggestion that you can actually extract CO2 and other greenhouse gases from the atmosphere. So this is a whole big question. It's certainly included in some of the IPCC, or most of the IPCC scenarios, that there's going to be what are called negative emissions, or that means sucking CO2 and other greenhouse gases out of the atmosphere. There's various ways in which that can be done. One is planting more trees, which is of course not a bad thing, except that you can't plant enough trees even to keep it down at the moment, the rate we're putting it in, let alone do the future as well. And also if it means that we're making countries particularly in the tropics, grow different sorts of trees than they traditionally use for their culture and food and things in order to sequester our carbon, that's not very reasonable. It's also dangerous as a strategy because it might give you the idea that you don't need to bother so much now because there will be some technologies down the line which will suck it out of the atmosphere, and so we'll all be all right. In fact, the technologies to extract CO2 out of the atmosphere some of them have been demonstrated. There are practical methods of extracting CO2, for example, from power station plants and then sequestering it, solidifying or liquefying it and sequestering it perhaps under the oceans. But I think it's a very dangerous strategy and that we shouldn't be relying on it. So this is what's called the emissions gaps. So we've got, this is historical emissions in black here up to about 2015. We've got the current policies in dark blue. This glitch here is the COVID effect with a little dip in 2020, but it's not going to last. If all the countries did what they said they would do with their national contributions, the difference would be that much. So I'm afraid it's the dark blue to the light blue. So it's great that they agreed something, but it's nothing like enough. And what we need, if we want to get temperatures to stay under 2 degrees warming, we need to do this yellow trajectory. And if we want to stay under 1.5 degrees, we need to do this green trajectory. So this is serious stuff, peaking very, very soon and really reducing as we go on. Now I realise I'm running out of time. The next big climate UNFCCC meeting was due to take place in Glasgow pretty much now, or even earlier this month. But of course, of COVID, it's been delayed till next year, and it's going to take place in November. And so we're really hoping that there's going to be more agreements on how countries can increase their ambitions on emissions reductions. And there's a lot of discussion now about who's doing what and when. So then you can get into the blame game. I think I'm not going to do this much. You can think about which countries are doing the most. The biggest emitter at the moment is China, you can see up here, followed by the USA and India. But, and there's some countries on a different vertical axis. If you now consider actually the per capita, which of course is a fairer way to do it, you get something that looks like this. So this is per person per year. It's also, this is consumption emissions, which takes account of the fact that when you import goods from a different country, those goods have got embedded carbon in that product. So the biggest, at least of the countries that I've chosen here, is the US of A. I think Saudi Arabia is bigger, but you can see the countries ranking here. So now, if you look, China is this brown colour. It's not as big as Europe at the moment. I mean, it's rising. So if there's a blame game, you know, we have to be very careful about what the rules are in this. We want all of these countries and all the others to reduce their emissions. So what's happening at the moment? Well, these are some recent news items. China is doing something. It said it's going to reduce its emissions to zero, get to net zero emissions by 2060, which is fantastic that it says that. Of course, it needs to say how it's going to do it, and that same criticism applies to all the other, or criticism or suggestion applies to all the other countries that are saying they're going to reduce their emissions. So we've had, just yesterday, the EU leaders have set a 55% target for CO2 emissions cut by 2030. We had Boris Johnson say he would do 68% emissions by 2030. And now President Trump is leaving. Joe Biden says he will rejoin the Paris Climate Agreement. Of course, Trump removed America from the climate agreement, but Joe Biden is going to rejoin and set an agenda in the US of A for reducing American emissions. So that's talking about nations, and of course we really do need the nations to do stuff, because they have the big control over what's going on. But if you personally want to do something about climate change, these are all some suggestions on the Grantham Institute website. Importantly, I think the most important one is talking about it to anybody who will listen. I'm afraid that's what I do. And also tell your MPs, your councillors, your local representatives that things need to be done and that you want it to be done. And actually there's some very good things that can come about. It's not just hair shirts and making things difficult. It makes the air cleaner. It's healthy for other reasons. You know, you have cleaner transport. There's plenty of co-benefits of acting on climate change, as well as the greenhouse gas emissions. So I'll stop there. Thank you.
Thank you so much for this amazing talk. Now it's time for Q&A. If you have any question, please